Okay. All right. Any questions about that? Anybody want to chat about those ideas about, you know, how to make life a little bit easier for yourself and better as you go? All right. Everything making sense? You able to take all that in? Can you give me a read? Everybody's good? Thank you. All right. Torin, you good? Mayumi? All right. Khaled, you got it all? Maybe I missed the thumbs. Thank you. Okay, cool. All right. So now let's talk just a little bit about different kinds of ways that you can tweak a linked list. The general stuff all works the same, but what are typical kinds of variants that you see in the world? So one is, as we've talked about, a doubly linked list. So in a doubly linked list, you're going to have a previous reference in addition to the next reference. So you've got one data reference, and then you've got one reference called next that points this way, and you've got one reference called previous that points that way, right? So each node carries two references. And as we said, the benefit is you can then, if you have an end reference as well as a front reference, you can start at the end and move this way. You can start at the front and move this way. If you're looking for something and you move this way and you went too far, you can then take the back one, the previous reference, and move back a node. So you can just move forward and backward with more ease with a doubly linked list. Okay. Do you need this for the project? No. Right? You really don't need a doubly linked list for this project. You can really start with the code that we wrote yesterday, right? You can start with very simple linked list code and then go from there. Okay. Do you want an end reference though? Yeah, maybe you want an end reference, right? That might be handy, but you can do that without having a doubly linked list. Okay. So also, as we talked about, some of the methods can then be simplified. If you have a search, maybe you know based on some a metric, like, you know, if you're doing alphabetical things, you could start from the end of the list if the thing is after a certain letter of the alphabet. Or if the number range is something that you know about, maybe you can start from one end versus the other. So some of the algorithms can, in fact, be a little bit simpler. Plus, of course, add at end, right? Add at front or add at end can both be very simple. If you have an end reference and you've got these double references, it's easy to add at the end, right? You don't even have to traverse to do that. So if you had a doubly linked list, you can go through your methods and shorten them quite a bit in some cases. Okay, so very typical. And again, your author's code is a doubly linked list with dummy nodes, right? With dummy nodes on each end. Okay. The other one that's interesting is a circular linked list, and that's of note because you want to use it in your project. And that is that the last reference here, K is the last letter of the alphabet in the student group, and notice that K points back to A. So A to C, C to H, H to K, K to A. So the thing that's interesting here is you can't look for the end of the list by looking for the next reference being null, right? What could you do instead? How are you going to know that you've made a full revolution and you're back at the start if you cared? How are you going to know that?
Make a reference saying where the front of the list is, and then when you get to that reference, then.
Right, and you already have a front reference, right? So
Right.
Front is already built in. So what you could do is you keep going around until the thing you are pointing at is the same thing that Front is pointing at, right? So I started at A, I'm now at C, I'm now at H, I'm now at K, but when I'm at K, notice I'm pointing at the same thing Front is pointing at. So you can make an equivalence here. Instead of saying, while current.next is not null, you can say, while current.next is not Front, right, is not pointing at the same thing as Front. So you certainly can know when you've gone back to the beginning, right, if you need to. But the interesting thing with a circular linked list is you can just go round and round, right? You can just go round and round. And there are a couple of cases where I think that is a super useful thing, right? And one of the places when I was thinking about this was, hey, isn't gameplay just really a great example of where a circular linked list is perfect? Because one player goes, then the next player goes, then the next player goes, and eventually you go back to the first player, right? It's just going to go round and round and round, and each player gets a turn. Now, certainly players get eliminated, but still, if one is thrown out, still you're going to go round and round and round. And in fact, you're going to go round and round until what happens? What's actually going to stop you in this scenario at the end of the game?
People will run out of strikes, isn't it?
When they run out of strikes, they get ejected. That's right. So yeah, the answer here is when only one is left, right? When size equals 1, you have a winner, right? So the way that you can loop is differently here. You're just going to go round and round and round, and you know the game is over when size is 1 because you've ejected all the other players, right? They're all gone. Make sense? But a circular linked list is perfect because it saves us the trouble of saying, oh, look, we got to the end of the list, so now we need to go start back at the beginning. Like, there's no code for that. It's just go to the next, right? Go to the next player. So I think that's kind of brilliant for gaming scenarios, is to use a circular linked list, which is where I got the idea, right? Make sense? Okay. So in terms of diagramming these things,